Hey everybody, now that we're familiar with fluid circuits, we're going to start talking about a similar phenomena, electric circuits. I have here a basic electrical circuit setup. It only consists of three things: a battery, a resistor, and an ammeter. We'll go through these one at a time. As you likely know, a battery just serves as the source of the electricity. In order to make electricity flow, there has to be energy to push electrons through the wires. This energy is provided by the battery. The resistor does exactly what its name implies. It resists the flow of electricity. Specifically, it takes energy from the moving electrons and turns it into heat. If you touch it, it's ever so slightly warm. The next piece is what is called an ammeter. An ammeter measures the amount of current that is flowing through the circuit. Unlike with a water circuit, we're not dealing with volumes of water passing by per time. Instead, we're talking about electricity. For electric currents, the unit of current is the amp. Based on this ammeter, we can see that the current flowing through the system is 101 milliamps. Remember, milli means a thousandth, so that's 101 thousandths of an amp, slightly more than 1/10. There's one other piece of equipment that we can use to analyze this circuit. This multimeter has been set to measure voltage. In the water circuit, pressure decreased as water passed through a pipe. The same thing happens here. When we have an object that resists the flow of electricity, such as this resistor, the voltage drops. Voltage in an electric circuit is a lot like pressure in a fluid circuit. The voltmeter currently reads 0.99 volts, roughly 1 volt. This means that the change in voltage from this side of the resistor to this side of the resistor is about 1 volt. For fun, let's replace this resistor with a light bulb. It's not very bright, but you can see that the electricity has caused the light bulb to light up. Let's do our measurements again and see if anything changed. The ammeter now reads 105 milliamps. In other words, the current has gone up ever so slightly. Let's check the voltmeter. The voltmeter now reads 0.96 volts. So why did those numbers change? Well, it turns out that the current passing through a system is related to two things: both the source of electricity, in this case the battery, which is not changing, but it also depends on anything in the circuit that is resisting the flow of charge. The light bulb resists the flow of charge just like the resistor. However, while the resistor only turns this energy into heat, the light bulb is able to turn some of this energy into light. The reason that the voltage and the current are different is that the resistance of the light bulb and the resistance of the resistor are not quite the same. Now we're going to do an example of how we can analyze a circuit to determine some interesting facts about it. I have here a basic circuit diagram. It contains only two pieces, a battery and a light bulb. Current is flowing this way around the circuit, from the positive terminal of the battery to the negative terminal of the battery, and the light bulb is lighting up. We have two pieces of information. We know that this is a 9-volt battery, and we know that this is a 50 ohm resistor. We want to know two things. First, what is the current passing through the system? Secondly, how much power is being produced by the light bulb? We have two equations to do this. The first is called Ohm's law, and it tells us how various circuit elements change the voltage in the circuit. The second equation is the power equation, which just tells us how much power a particular circuit element produces. Let's start by determining the current in the circuit. Just as when we were doing pressures in fluid, we always apply Ohm's law between 2 points of the circuit. One of the things that's really nice about a circuit, though, is we can pick the same beginning and ending point. When we do this, the total change in voltage is 0. If you start here, go all the way around the circuit and get back to where you started, you would expect that the voltage will be the same. So let's apply that here and see if we can figure out the current in the circuit. Let's pick this corner of the circuit to be our initial and final point, and then let's track the current around the circuit and find out what all these values need to be. Epsilon represents any increase in voltage caused by a battery. In this case, as we pass from this corner to this corner, the battery increases our voltage by 9 volts. So this term is 9 volts. Next, we have to pass by the resistor. We don't know the current in the resistor, but we do know its resistance. It's 50 ohms. We have to add on an IR term for every element in the circuit that is not a battery. Because the light bulb is the only thing in the circuit besides the battery, we only have one term. Again, we don't know the current yet, but we're going to find it. What is this equal to? Well, we already said that we were starting and ending at the same place. The voltage at this point always has to be the same. So the total change in voltage as we go all the way around the circuit once is just 0. Now we can solve this equation to determine the current passing through the system. And there we have it. The current passing through this circuit is 0.18 amps. Next, we want to know the power dissipated by this light bulb. We have two equations for power. One says that the power is equal to the current passing through the light bulb times the change in voltage across the light bulb. And the other says that the power is equal to the change in voltage squared divided by the resistance. Both work. They'll give you the same answer. We'll use this one for the purposes of this video. Something to note is that delta V is always the change in voltage across the specific circuit element that you're considering. In this case, we only have one circuit element, so this is not ambiguous. However, in most circuits, you're going to have more than one thing in the circuit. So you will need to determine the change in voltage across the individual pieces in the circuit in order to do this kind of analysis. We'll see plenty of these kinds of examples in the future. For now, we'll just proceed with the single circuit element. The first question we need to ask ourselves is, what is the change in voltage across this light bulb? Well, let's go back and consider how we determined the current flowing through the circuit. We did this by starting at this corner and going around the circuit once, and noting that if we get back to the place we started, the total change in voltage must be 0. Doing that analysis again, we know that the battery increases the voltage by 9 volts. If we want to get back to where we started, the light bulb must decrease the voltage by 9 volts, such that as we go all the way around the circuit, the total change in voltage is 0. So now we know our change in voltage across our light bulb. It's just negative 9 volts. We also know the resistance of the light bulb. It's just 50 ohms. We can now plug these numbers into the power equation to determine the power released by the light bulb. And there we go. The power released by this light bulb is 1.62 watts. A watt is just a joule per second. So saying that the light bulb releases 1.62 watts is the same thing as saying that every second the light bulb releases 1.62 joules of energy. We're going to see lots of examples of circuits in the future, and most of them are going to involve more than one circuit element. Getting good practice with simple circuits will come in handy when we get to much more complicated examples involving more than one circuit element and potentially more than one route for the electricity to take.